The universe began in a silent, searing darkness. Before stars or planets, a chaotic soup of particles forged the very first atomic nuclei. This was the silent birthplace of elements, a hidden factory where the universe conducted its first fusions. By the end of this journey, you will understand the ancient origin of every atom in your body. We will uncover why this frantic process stopped after just 3 minutes and how a single fragile particle acted as the universe's most critical bottleneck. What does it mean that our existence hinges on events from the very first moments of time? That initial canvas was a roiling sea of pure energy, a quark-gluon plasma so hot and dense that the fundamental building blocks of matter could not even cling together. For a fleeting moment, the universe was a soup of free quarks and gluons, the ingredients of protons and neutrons, not yet able to form the particles themselves. Then came the expansion, the great cooling. In less than a millionth of a second, the temperature dropped just enough, crossing a critical threshold. It was like a cosmic freeze where individual water molecules suddenly lock into ice. Quarks, once free, were now bound together into the first stable protons and neutrons. This was the true birth of matter, the moment the universe gained its tangible substance. But this delicate process was a razor's edge. Had the universe expanded and cooled even a fraction faster, quarks would have been flung too far apart to ever combine. The result would have been a cosmos filled with nothing but solitary hydrogen, a universe of simplicity with no path to planets or life. The precise rate of that initial expansion was the first and most critical act of cosmic fine-tuning, setting the stage for everything that was to follow. A frantic cosmic clock was now ticking. The universe was a mere second old, and the temperature was still an unimaginable several billion degrees. In that incredible heat, any attempt to build something more complex than a single proton was instantly demolished. High-energy photons, particles of light, roamed freely, smashing any fledgling nucleus back into its constituent parts with relentless force. It was a world where creation was impossible. But then, the great expansion continued its work. The temperature plummeted, falling from billions to millions of degrees in a matter of minutes. Suddenly, a narrow window of stability cracked open. This fleeting era is known as Big Bang Nucleosynthesis, the universe's very first and most dramatic nuclear fusion workshop. The density was still incredibly high, but it was dropping fast. This created a desperate race against time. Protons and neutrons had to find each other, collide, and stick together before the expanding cosmos diluted their chances forever. Picture an assembly line moving at a breakneck speed, with workers frantically trying to assemble parts before the conveyor belt carries everything out of reach. The entire process, from the first fusion reaction to the final one, was over in roughly 3 minutes. In those 180 seconds, the fundamental chemical identity of the entire cosmos was set. The outcome of this frantic race would determine what the universe was made of for billions of years. The race began with the most fragile of partnerships. A single proton and a single neutron managed to cling together, forming the very first deuterium nucleus. This was not a sturdy building block, but a precarious bridge. Deuterium is an isotope of hydrogen, but its bond is astonishingly weak. In the searing heat of the young universe, high-energy photons, the very particles of light, acted like a constant cosmic wrecking crew. For a critical period, every time a proton and neutron tried to form a deuterium nucleus, it was immediately blasted apart. The entire cosmic assembly line was stuck, unable to proceed past this first essential step. The universe was filled with the raw materials for creation, but it was trapped behind a door it could not yet open. Everything hinged on the temperature dropping to a precise value. Finally, as the cosmos expanded and cooled past around 1 billion degrees, a pivotal shift occurred. The destructive power of the photons faded just enough. For the first time, the rate of deuterium formation began to outpace its destruction. This was the moment the dam broke. The existence of a stable deuterium bridge allowed the nuclear chain reaction to flood forward. This single, fragile nucleus was the gateway. Without it, the universe would have remained a soup of isolated hydrogen, forever simple. Its successful formation was the universe's first tentative step from utter simplicity toward the potential for complexity. Today, the deuterium we can still find in interstellar space and in the water on Earth is a direct relic of that narrow 3-minute window. It is a cosmic fossil, and its abundance is a powerful clue. Think of deuterium as a baryometer, a precise instrument that measures the density of ordinary matter in the early universe. The amount of deuterium we see is incredibly sensitive to how many protons and neutrons were jostling around during Big Bang Nucleosynthesis. Too many particles and all the deuterium would have been quickly fused into heavier elements, leaving almost none behind. Too few, and the reactions would have sputtered, also leaving a different abundance. The fact that we find the precise amount we do is a stunning confirmation of our cosmic models. It tells us that the density of matter was perfectly tuned to allow this fragile bridge to form and for the chain of creation to begin. With the deuterium bottleneck finally broken, the universe's assembly line roared to life. Protons and neutrons, now linked by that fragile deuterium bridge, began a rapid and relentless chain of fusion. This was a cascade of creation, with deuterium nuclei eagerly colliding with more protons and neutrons to form helium-3 and then, in a final, decisive step, helium-4. This new nucleus, with its 2 protons and 2 neutrons, was a marvel of stability. Its formation released a surge of binding energy, locking the particles into an arrangement so strong and efficient that it became the ultimate destination for nearly every free neutron in the cosmos. The universe's frantic 3-minute workshop was designed to produce one primary product above all others, and that product was helium-4. This process was breathtakingly thorough. Almost every single neutron that had formed when the universe was just 1 second old was swiftly captured and sealed inside a helium-4 nucleus. The efficiency was so absolute that it left a permanent, predictable mark on the cosmos. When the final fusion reaction ceased, roughly 1/4 of the ordinary matter in the universe by mass was locked up in this newly forged helium. The rest remained as single, unbound protons, which are the nuclei of simple hydrogen. This prediction that the oldest stars and the most primordial gas clouds should be about 25% helium is not just a neat idea. It is a foundational pillar of the Big Bang theory, and modern astronomical observations match this prediction with stunning accuracy. This universal helium abundance is a direct echo from the first 3 minutes, a fossilized ratio that confirms our deepest cosmic models. The creation of helium-4 represented the pinnacle of the universe's early manufacturing capabilities. It was a testament to the robust, perfect nature of this particular nuclear arrangement. Yet, this very success also marked a hard limit. In its rush to build this stable, efficient nucleus, the universe consumed almost all of its available building blocks. The initial burst of fusion created a new cosmos, one with a clear and simple chemical identity, dominated by hydrogen and helium. This was the baseline composition for everything that would follow, a cosmic canvas painted with only the 2 lightest and simplest of elements. Yet this cosmic factory had one more, far more subtle product. Alongside the vast quantities of helium-4, the furious chain reactions forged a minuscule amount of a heavier element, lithium-7. For every 10 billion atoms of hydrogen, only a handful of lithium nuclei were created. This was a mere trace, a ghostly signature left over from the first 3 minutes. But this tiny amount has become a colossal problem. Our most sophisticated models of Big Bang Nucleosynthesis predict a specific abundance of this primordial lithium. Yet when astronomers measure the oldest stars in our galaxy, stars that formed from the pristine, uncontaminated gas of the early universe, they find only about 1/3 of the lithium that the models say should be there. The stars contain 3 times less lithium than our cosmic recipe calls for. This is the cosmological lithium problem, a stubborn and glaring discrepancy that has persisted for decades. It is a major unsolved mystery in modern cosmology. How could our understanding of the universe's first moments be so spectacularly successful in predicting the amounts of hydrogen, deuterium, and helium, and yet fail so noticeably for this one tiny element? The discrepancy suggests a crack in our otherwise solid model. Perhaps our knowledge of nuclear physics under the extreme, searing conditions of the first few minutes is still incomplete. Maybe a key nuclear reaction rate needs a slight adjustment, one that would have allowed more lithium to be destroyed than we currently calculate. Or, more profoundly, it might point to the influence of something entirely new. Some theoretical physicists have proposed that exotic, unknown particles from the earliest moments, such as certain types of dark matter, could have interacted with the primordial soup, subtly altering the nuclear chain and consuming the missing lithium. The lithium problem is a powerful and humbling reminder. It tells us that even our most successful and well-tested models of the cosmos have frontiers yet to be explored. This tiny trace element, this cosmic afterthought, poses a massive question at the very foundation of our story. If we cannot account for the precise amount of lithium forged in the silent birthplace of elements, what other secrets is the early universe still keeping? And so the great cosmic factory fell silent. The frantic fusion frenzy that had defined the first 3 minutes of existence came to an abrupt and final halt. The universe's relentless expansion was the ultimate off-switch. As space stretched, the density of matter plummeted, and with it, the temperature. It crossed a critical threshold, falling below the point where atomic nuclei could overcome their mutual electrical repulsion and fuse together. The particles were simply too far apart and moving too slowly to collide with any meaningful force. The assembly line didn't just slow down, it shut down completely. The free neutrons, the essential catalysts for building anything beyond hydrogen, were now almost entirely gone. Most were securely locked inside the stable hearts of helium nuclei. The few that remained free would decay away within minutes, transforming into a proton, an electron, and a ghostly neutrino. With the neutrons gone and the protons left to repel each other, the path to creating anything heavier was permanently blocked. The universe was left with a frozen, fossilized composition. Roughly 75% of its ordinary mass was hydrogen, the single protons that never found a neutron to fuse with. The other 25% was the helium-4 that had been so efficiently manufactured, and scattered through this primordial gas were the ghostly traces of deuterium, helium-3, and that puzzling, minuscule amount of lithium-7. This was the final product, the ultimate chemical legacy of the Big Bang itself. For the next several 100 million years, no new elements would be created anywhere in the cosmos. The universe entered a profound and silent dark age, a period where these first elements simply drifted in an expanding sea of darkness. this great shutdown was not a failure but a necessity. It preserved the pristine signature of those first 3 minutes like a cosmic time capsule. Because fusion stopped so decisively, the elemental mix was frozen in place, allowing us, billions of years later, to look at the oldest stars and clouds of gas and see that original recipe. That silence was the pause that made everything else possible. It allowed gravity to slowly, patiently, gather these primordial atoms, these hydrogen and helium building blocks, into the vast, dark clouds that would eventually collapse to ignite the very first stars. But how can we be so certain about events from the very first minutes? Our evidence comes from a ghostly whisper of ancient light that fills every corner of the cosmos. This is the cosmic microwave background radiation, the afterglow of the Big Bang itself. Think of it as the universe's baby picture, taken when it was a mere 380,000 years old. Before this moment, the universe was a hot, opaque fog. Protons and electrons were separate, constantly scattering light, making the entire cosmos as impenetrable as the heart of a star. But as expansion cooled the universe, a pivotal transition occurred. Electrons were finally captured by atomic nuclei, forming the first neutral atoms. Suddenly, the fog lifted, the universe became transparent, and that primordial light, which had been trapped and bouncing around for eons, was finally set free. That first flash of liberated light is what we detect today as the cosmic microwave background. It is the oldest light we can ever see, a fossilized snapshot of the infant universe. While this light was released hundreds of thousands of years after nucleosynthesis ended, it carries a perfect imprint of the conditions that the nuclear reactions depended on. The key is in the subtle patterns within this light. When we map the cosmic microwave background with satellites, we don't see a perfectly uniform glow. Instead, we see tiny, minuscule variations in temperature, like a cosmic fingerprint. These hot and cold spots are the seeds of all future structure, the gravitational blueprints for galaxies and clusters. But they are also a precise cosmic scale. The exact size and distribution of these fluctuations tell cosmologists with incredible accuracy the total density of ordinary matter that existed in the early universe. This number, read from the ancient sky, is then plugged directly into our equations for Big Bang Nucleosynthesis. The result is nothing short of spectacular. The amount of ordinary matter measured from the light echo perfectly predicts the exact primordial abundances of hydrogen, deuterium, and helium that we observe in the oldest stars and gas clouds. It is a triumphant convergence of evidence, two completely independent lines of inquiry, one studying the first 3 minutes through elemental fossils, and the other studying the universe at 380,000 years through ancient light, tell the very same story. The cosmic microwave background is our ultimate witness, confirming that the silent birthplace of elements was a real, physical event whose signature is forever woven into the fabric of space. But the story of the first 3 minutes is not just about the particles we can easily see. It also involves the most ghostly participants in all of physics, neutrinos. In that first searing second, the universe was so dense that even these phantom particles, which today can pass through light years of lead without a bump, were trapped. They were tightly coupled with protons, neutrons, and electrons, a churning, interactive soup. This intimate contact gave neutrinos a profound influence over the cosmic environment itself. They contributed to the radiation pressure that was fighting against gravity, subtly controlling the rate at which the universe expanded and cooled in its earliest moments. The number of different types or families of neutrinos was a critical variable. More families would have meant more radiation pressure, causing the universe to expand faster. A faster expansion would have slammed the nuclear fusion window shut even sooner, dramatically altering the final mix of hydrogen, deuterium, and helium. The primordial abundances we observe today are a perfect match for a cosmos with exactly 3 families of light neutrinos. This is a stunning convergence. The chemistry of the oldest stars confirms a fundamental prediction of particle physics, a discovery made not in a giant underground laboratory, but by reading the fossilized elements from the Big Bang. Beyond setting the expansion rate, neutrinos had one more, even more direct role to play. They were the masters of a cosmic transmutation. Through the weak nuclear force, neutrinos were constantly interacting with neutrons and protons, turning one into the other. A neutron could absorb a neutrino and spit out an electron, becoming a proton. A proton could absorb an antineutrino and emit a positron, becoming a neutron. This delicate dance of conversion set the initial neutron-to-proton ratio just before nucleosynthesis began. That single number, the ratio of neutrons to protons, was the fundamental fuel gauge for the entire helium production line. When the universe cooled enough for this neutrino-driven swapping to stop, it left behind precisely 1 neutron for every 7 protons. This was the exact amount of raw material needed for the frantic 3-minute fusion frenzy to produce the 25% helium abundance we see across the cosmos. These ghost particles, nearly massless and famously aloof, were the silent architects of our elemental universe. Their subtle touch in the first second wrote the recipe that everything else would follow. But this entire cosmic genesis rests on a puzzle so deep it challenges our understanding of reality. Why did any of this matter survive to fuse in the first place? The laws of physics, as we understand them, suggest the early universe should have been perfectly symmetrical, creating matter and antimatter in equal amounts. For every proton born, an antiproton should have been created. These are not mere opposites, they are perfect mirrors that annihilate each other on contact, converting their mass into a flash of pure energy. In that first chaotic moment, a great annihilation should have occurred. Every particle of matter should have met its antimatter twin, vanishing in a storm of light. The final result of the Big Bang should have been a universe containing nothing but photons, a featureless sea of radiation expanding forever into emptiness. There would have been no protons, no neutrons, no raw material for nucleosynthesis. The silent birthplace of elements would have been stillborn, and yet here we are. Clearly, that is not what happened. Something went wrong with the perfect symmetry. For every 1 billion pairs of matter and antimatter that annihilated each other in that primordial inferno, a single, solitary particle of matter was left behind. 1 in a billion, that is the entirety of the excess, the tiny, inexplicable surplus that makes up our entire reality. Every star, every planet, and every atom in your body exists only because of that 1 part in a billion preference for matter. This is the Barrian asymmetry, the universe's most consequential accounting error. It is the reason we have a cosmos filled with things instead of a cosmos filled with light. Without this slight imbalance, the frantic nuclear fusion of the first 3 minutes would have had nothing to build with. The universe would have remained eternally silent, with no elements to speak of. The origin of this bias remains one of the greatest mysteries in all of science. What natural law could have favored matter over antimatter by such a tiny, yet universe-defining margin? The answer lies somewhere in the physics of the very first fractions of a second, in conditions so extreme that the fundamental forces themselves were unified. Solving this mystery means peering into a realm beyond our current reach, a time when the universe decided, for reasons we do not yet comprehend, to choose substance over silence. This numerical precision transforms the entire cosmos into a grand laboratory. The equations of Big Bang Nucleosynthesis are deceptively simple in their inputs. Cosmologists need to know just one number, the density of ordinary matter in the early universe. They plug this single value into a set of nuclear reaction rates, equations that describe how protons and neutrons fuse and break apart. The output is a set of very specific predictions for the final chemical composition of the universe. The model tells us exactly how much hydrogen should remain, how much helium-4 should have been forged, and the precise, tiny fractions of deuterium and lithium-7 that are the signature of that frantic 3-minute window. But a prediction is just an idea until it is tested against reality. The search for this evidence takes astronomers to the farthest reaches of space and time. They point their telescopes toward the most ancient stars in the halo of our galaxy, celestial fossils that formed from gas that was never polluted by later generations of stars. They analyze the light from these old suns, reading the chemical fingerprints in their atmospheres. They also look at the most primordial gas clouds in the distant universe, pristine pockets of matter that have remained untouched for billions of years. The results of this cosmic audit are breathtaking. The observed abundance of deuterium, that fragile bridge element, matches the theoretical prediction with an accuracy of just a few percent. The universal fraction of helium-4, that 25% by mass, aligns perfectly with what the equations foretold. This is not a vague correspondence. It is a precise, quantitative agreement between the nuclear physics we study in particle accelerators on Earth and the chemical makeup of the most ancient objects we can observe in the sky. This success turns the universe itself into a proving ground. It demonstrates a profound and beautiful connection. The laws that govern the interactions of subatomic particles, the rules of the quantum world, are directly responsible for the large-scale chemical history of everything we see. The silent nuclear reactions of the first 3 minutes wrote a signature that we can still read today, and the numbers match. This gives us an immense confidence in our ability to reconstruct the ancient past, to peer back across nearly 14 billion years and understand the very first fusions that set the stage for our existence. This fundamental roadblock in nuclear physics explains the universe's chemical simplicity at its birth. The frantic assembly line of the first 3 minutes ran headlong into a wall, a gap in the very architecture of matter itself. The problem was a missing link. There are no stable atomic nuclei with a mass of 5 or 8. Imagine trying to build a tower where every 5th and 8th brick is made of a substance that instantly crumbles to dust. This was the impossible challenge the early universe faced. A helium-4 nucleus, the primary product of Big Bang fusion, is incredibly stable. But try to add one more proton to it, creating a hypothetical lithium-5, and the new nucleus is so unstable it disintegrates in a fraction of a nanosecond. The same fate meets any attempt to add a neutron. The mass 5 barrier was utterly impassable. The only other potential path was to fuse 2 helium-4 nuclei together. This collision does occur, but it only produces beryllium-8, a nucleus with a mass of 8 that is even more spectacularly unstable. It exists for less than a trillionth of a second before flying apart into 2 helium nuclei again. With no stable nuclei at mass 5 or 8, the entire chain reaction of fusion ground to an abrupt and final halt at lithium-7. The cosmic factory had reached its built-in ceiling. The frantic activity of the first 3 minutes could not produce carbon, oxygen, iron, or any of the other elements essential for planets and life. The universe was left with a skeleton crew of elements, a simple palette of hydrogen, helium, and trace amounts of lithium. This nuclear bottleneck forced the cosmos into a long, silent waiting period. the creation of heavier elements had to be postponed for hundreds of millions of years until the first stars ignited in their furnaces. Only in those stellar crucibles, under crushing gravitational pressures and searing temperatures far beyond anything in the early universe, could a special process overcome this gap. Inside stars, the instability of beryllium-8 becomes the key. The density is so high that before a beryllium-8 nucleus can decay, it can sometimes be struck by a third helium nucleus. This rare three-part collision, known as the triple alpha process, forges stable carbon. It is a delicate dance that bypasses the roadblock entirely. But this process was impossible in the rapidly expanding and cooling Big Bang. The density dropped too fast for such a statistically unlikely event to occur. So the silence of that first birthplace was not an accident. It was a direct consequence of a fundamental limitation written into the laws of nuclear physics, a cosmic pause that made the eventual fiery birth of the stars absolutely necessary. To witness the universe's first 3 minutes, we must turn our gaze to the glowing screens of supercomputers. These vast machines are our time machines, running the intricate equations of computational cosmology. Scientists program them with the known laws of physics, the nuclear reaction rates we've measured in laboratories, and the initial conditions of a hot, dense cosmos. The simulation then begins, tracking the fate of billions of digital particles as the virtual universe expands and cools in a fraction of a second. It is a frantic digital dance, calculating every possible collision and fusion across a complex network of hundreds of nuclear pathways. Each run of the simulation is a new experiment, a test of our cosmic model against the ultimate evidence, the fossilized abundances we see in the oldest stars. What happens if we slightly change the density of matter? What if a particular nuclear reaction occurs a little faster or slower than we thought? The computer answers these questions by spitting out a final chemical composition, a predicted universe that we can then compare to our own. This process of tweaking and testing is how we refine our story, homing in on the precise sequence of events that must have occurred. These digital recreations have become indispensable, especially for tackling stubborn mysteries like the cosmological lithium problem. Researchers can simulate the early universe with different types of exotic particles or adjusted nuclear physics, searching for the specific conditions that would leave behind the low amount of lithium we actually observe. It is a digital detective story playing out in lines of code and vast data sets. By bringing the silent birthplace to life on our screens, computational cosmology does more than just confirm our theories. It allows us to explore the roads not taken, to ask what kind of universe would have emerged if the fundamental constants had been just a little bit different. It transforms our cosmic history from a fixed narrative into a living, breathing simulation, one that continues to reveal the delicate balance that made our existence possible. The success of the Standard Model is undeniable, yet its one glaring flaw, the lithium problem, acts as a powerful beacon, drawing scientists toward more radical possibilities. Our understanding of the universe's first moments is being actively stress-tested by a host of alternative theories. One compelling line of inquiry suggests the early cosmos was inhabited by exotic, unknown particles. Imagine a heavy, unstable particle, a relic from an even earlier epoch, decaying during or just after nucleosynthesis. Its death throes could have flooded the primordial soup with a burst of extra neutrons or a shower of high-energy radiation. This sudden injection would have been like throwing a wrench into a perfectly timed assembly line, potentially disrupting the delicate chain of reactions that produced lithium-7, either by destroying more of it or by preventing its formation in the first place. This is not science fiction. It is a serious proposal to make the mathematical models match the astronomical observations. other physicists explore an even more profound possibility that the fundamental constants of nature are not truly constant. What if the strength of the nuclear force was slightly different in that searing hot first few minutes? A change of even a fraction of a percent in these foundational numbers would have a dramatic effect on nuclear cross-sections, which is just a technical term for how likely particles are to collide and stick together. A slightly stronger force might have allowed reactions to proceed faster, burning up the problematic lithium before the universe cooled. These alternative scenarios are crucial exercises in scientific humility. They force us to ask whether the laws we take for granted today were absolute in the extreme environment of the Big Bang. By rigorously exploring these cosmic what-ifs, we are not abandoning the standard model. We are fortifying it, probing its limits to see where it might flex or break. This relentless quest ensures that our reconstruction of the universe's silent birthplace remains a living, breathing investigation, one where a single stubborn anomaly can illuminate the path to a deeper, more complete truth. So the universe waited, holding its simple recipe of hydrogen and helium in the expanding dark. This quiet period was a necessary prelude, a gathering of cosmic breath before the next great act of creation could begin. The silent birthplace had provided the raw materials, the fundamental seeds from which all complexity would eventually grow. It was gravity that finally broke the silence. Slowly, patiently, its invisible hand began to pull at the vast, dark clouds of primordial gas. It drew hydrogen and helium together into ever denser knots, compressing them until the very centers of these clouds ignited under unimaginable pressure. The first stars were born. These were not like the stars we see today. Astronomers call them population 3 stars, and they were fundamentally different, composed of nothing but the pristine elements from the Big Bang itself. Pure hydrogen and helium. This pure composition made them titans. Without heavier elements to help radiate heat away, these first stars had to collapse to incredible densities and masses to trigger fusion, likely becoming behemoths hundreds of times more massive than our Sun. Their lives were spectacularly brilliant and brutally short. Within them, a new chapter of cosmic alchemy began. Stellar nucleosynthesis took over where the Big Bang's fusion frenzy had been forced to stop. The crushing gravity and searing temperatures at the core of a star created a sustained, stable furnace, an environment the rapidly cooling early universe could never provide. Here, the nuclear bottleneck that halted progress at Lithium was finally overcome. Through a delicate and rare process called the triple alpha process, 3 helium nuclei could collide in quick succession, bypassing the unstable mass 8 barrier to forge stable carbon. This was the universe's great leap forward. With carbon as a new foundation, fusion could march steadily up the periodic table. Helium nuclei fused with carbon to create oxygen. Further reactions built neon, magnesium, and silicon, layer by layer, like an onion forming shells of heavier elements. This second generation of element production was building the very stuff of planets and life, all from the hydrogen and helium foundation laid down in the first 3 minutes. The journey culminated at iron. Fusing elements up to iron releases energy, powering the star and keeping it stable. But creating any element heavier than iron requires energy. It consumes power rather than providing it. This is the stellar death sentence. Once a star's core turns to iron, its engine sputters and fails. For those first massive stars, the end was swift and catastrophic. They exploded as supernova, scattering their newly forged riches carbon, oxygen, silicon, iron across the void. These stellar explosions were more than just an end. They were the final, essential step, seeding the cosmos with the ingredients for rocky planets, for water, and for life itself. Every element in your body that is heavier than iron, like the gold in a ring or the iodine in your body, was forged in the even more extreme violence of these stellar deaths or the collisions of neutron stars. The silent birthplace gave us a universe, but it was the fiery lives and deaths of the first stars that gave that universe a future. We have never directly seen the first generation of stars, but their ghostly signature is all around us, written in the chemical code of the ancient suns we can observe. This is cosmic archaeology, where astronomers act as celestial historians, sifting through the stellar population of our galaxy's halo to find the oldest surviving relics. They are hunting for what are known as extremely metal-poor stars. In the language of astronomy, the term metal has a very specific meaning. It refers to any element heavier than helium. So a star with low metallicity is one that contains only a tiny, trace amount of elements like carbon, oxygen, or iron. These stars are the living fossils of our cosmic neighborhood. They formed from gas clouds that had been seeded by just one or two previous generations of supernova, getting us as close as we can possibly get to the pristine, primordial conditions just after the Big Bang. When we point our telescopes at one of these ancient suns and break its light down into a spectrum, we are reading its chemical autobiography. Each dark line in that rainbow of starlight is the unique fingerprint of a specific element. The pattern and depth of these lines tell a profound story. They reveal not just what the star is made of, but what the cloud it was born from was made of. If we find a star with a minuscule amount of iron but a surprising overabundance of carbon, that is a direct clue. It tells us that the supernova which enriched its birth cloud was a very specific type of star, one with a particular mass and explosion mechanism that favored carbon production over iron. This is how we indirectly study the lives and deaths of the very first stars, stars we will never see directly. By connecting the chemical dots from these ancient stellar fossils back to the silent forges of the Big Bang, we are slowly reconstructing the entire evolutionary chain of our universe, from its first silent breath to the complex, element-rich cosmos we call home. This silent, finely tuned recipe of hydrogen and helium points toward a deeper, almost unsettling truth about our cosmos. The specific outcomes of Big Bang nucleosynthesis were not random. They were dictated by the universe's fundamental operating manual, the unchangeable numbers we call physical constants, the strength of gravity, the power that binds atomic nuclei together, the masses of protons and neutrons. These are not variables. They are fixed features of reality, and if any one of them had been even slightly different, the entire cosmic story would have ended before it began. Consider the strong nuclear force, the glue that holds protons and neutrons together in a nucleus. If this force were just a few % weaker, the deuterium bottleneck would have become an insurmountable wall. That first fragile bridge between a proton and a neutron would have been too weak to form, or so unstable it would have shattered instantly. The entire chain of fusion would have never started. The universe would have remained a monotonous sea of hydrogen with no heavier elements, no stars, and no planets. Conversely, if the strong force were significantly stronger, the initial nuclear reactions would have been too efficient. Protons and neutrons would have fused into heavier elements with reckless abandon, potentially consuming all the hydrogen fuel. Without vast reservoirs of hydrogen to burn for billions of years, long-lived stable stars like our Sun could never have formed. The universe would have been filled with short-lived, unstable stellar furnaces, incapable of nurturing the slow, delicate process of life. This delicate balance leads to a profound philosophical concept known as the anthropic principle. In its simplest form, it suggests that the universe we are capable of observing must, by necessity, have the properties that allow for our existence. We are here to ask questions about the cosmos because the cosmos was built in a way that permits creatures like us to exist. The silent birthplace of elements was not just a physical event. It was a selective filter. Out of all the possible universes that could have been born with different constants and different laws, ours was one that produced the precise chemical palette required for complexity. The hydrogen that fuels stars, the helium that allows for efficient fusion, the deuterium that acts as a cosmic fossil, all of these were forged in amounts that make our reality possible. Our existence is inextricably linked to the nuclear reactions of the first 3 minutes. We are not just living in this universe, we are a product of its most ancient and precise manufacturing process. The same nuclear reactions that define the cosmos in its first 3 minutes are now being recreated in laboratories here on Earth. To truly understand the silent birthplace of elements, scientists must become cosmic alchemists themselves, using giant machines called particle accelerators. These are not merely telescopes, they are time machines that allow us to probe the fundamental forces at play when the universe was just a newborn. Inside these vast circular tunnels, physicists accelerate beams of atomic nuclei to nearly the speed of light and smash them together. The goal is to measure with painstaking accuracy the exact probability that two specific nuclei will fuse when they collide. This probability is known as a nuclear reaction rate, and it is the most critical number for any model of Big Bang nucleosynthesis. For instance, the rate at which a deuterium nucleus and a proton fuse to form helium-3 is a linchpin in the entire chain of events. A tiny change in this measured rate would ripple through the entire simulation, altering the predicted amounts of primordial deuterium and helium we expect to see in the cosmos. These experiments are a monumental technical challenge. Researchers must replicate the immense energies of that searing first few minutes, while dealing with reaction probabilities so vanishingly small they are like searching for a single, specific grain of sand on an entire beach. Detecting these rare events requires exquisitely sensitive equipment and a great deal of patience, often allowing the accelerator to run for weeks to gather just a handful of usable data points. Yet this tedious, earth-bound work is what transforms cosmology from a beautiful story into a precise, quantitative science. Every new measurement from a lab like this directly feeds into the supercomputer simulations, tightening the bolts on our cosmic models and reducing their uncertainties. The ghostly whisper of the Big Bang is clarified by the loud, definitive crash of particles in a detector. This is the powerful synergy of modern science, where the largest questions about the universe are answered by the most meticulous experiments on our own planet. Deuterium is a cosmic fossil of unparalleled purity. This fragile isotope of hydrogen, forged only in the first 3 minutes, carries a story that helium and lithium cannot. While helium is also manufactured in the hearts of stars and lithium can be consumed by them, deuterium is uniquely vulnerable. Its weak nuclear bond is easily shattered by the intense heat of any stellar environment. Whenever deuterium falls into a star, it is destroyed. This simple, brutal fact makes it an impeccable cosmic diagnostic. Every single deuterium nucleus we detect in the local interstellar gas of our galaxy, or in pristine clouds at the edge of the observable universe, must be a direct survivor from the Big Bang itself. It is a relic that has been carefully preserved, a drop of the primordial ocean that has never been boiled away. Astronomers use it as a baryometer, a precise instrument to measure the density of ordinary matter throughout cosmic history. They point their telescopes at distant quasars, using their brilliant light as a cosmic flashlight. As this light travels through ancient clouds at the edge of the observable universe, must be a direct survivor from the Big Bang itself. It is a relic that has been carefully preserved, a drop of the primordial ocean that has never been boiled away, a astronomer's use it as a barometer, a precise instrument to measure the density of ordinary matter throughout cosmic history. They point their telescopes at distant quasars, using their brilliant light as a cosmic flashlight. As this light travels through ancient clouds of gas on its way to us, deuterium atoms within those clouds absorb specific telltale wavelengths. The depth of these absorption lines reveals exactly how much deuterium was present in that region of space billions of years ago. The stunning result is a story of consistency. Whether we look at a gas cloud 10 billion light-years away or the diffuse matter in our own galactic neighborhood, the measured deuterium abundance aligns perfectly with the predictions from Big Bang Nucleosynthesis. This isotopic fingerprint, found unchanged across the vast expanse of space and time, is a powerful confirmation of our standard model. It tells us that the density of ordinary matter has been a constant thread woven through the cosmos, a fundamental parameter set during those first explosive minutes. In the silent chorus of primordial elements, deuterium sings the clearest, most untouched song of our cosmic origin. But what if another, invisible player was present in that silent birthplace? The influence of dark matter, that mysterious substance which makes up most of the universe's mass, might have reached back into those first few minutes. Most of our standard models treat dark matter as a ghost, interacting only through the force of gravity, yet some compelling theories suggest a more complex story. What if certain types of dark matter particles were not completely inert? If they could annihilate each other or decay during the frantic epoch of nucleosynthesis, the effect would have been profound. Such events would have injected a fresh burst of energy into the cooling cosmic soup. Think of it as throwing a new log onto a dying fire. This extra heat would have altered the universe's thermal history, potentially slowing its cooling rate for a brief moment. That single change would have rippled through the entire nuclear assembly line. A longer window of intense heat could have allowed more time for nuclear reactions to burn up deuterium, or it might have altered the delicate balance that set the final helium abundance. The primordial elements we measure today are therefore a cosmic ledger, recording any such interference. The fact that the observed abundances of deuterium and helium match our predictions so perfectly places a powerful constraint on dark matter. It tells us that whatever dark matter is, its particles must not have significantly disturbed the thermal environment of the first 3 minutes. They could not have been too massive, too interactive, or too prone to decay. The silent birthplace of elements becomes a unique laboratory, a testbed for physics far beyond the standard model. The pristine nuclear fossils from the dawn of time are silently testifying against entire classes of theoretical dark matter particles, ruling them out with the quiet authority of ancient evidence. The silent birthplace of elements was not an isolated event, but a single, decisive chapter in a far grander cosmic story. To understand its true significance, we must see it within the vast timeline of the universe, a sequence of epochs that built our reality one upon the other. It all began with the Planck epoch, a realm so far beyond our comprehension that time and space as we know them did not yet exist. From that initial singularity, the universe inflated in a fleeting, exponential growth spurt, smoothing and stretching the fabric of space itself. As this inflationary era ended, its energy transformed, flooding the cosmos with a searing, dense soup of fundamental particles, the quark-gluon plasma. This was the raw material of existence, a chaotic sea where the ingredients of matter were not yet assembled. Then came the great cosmic freeze, as expansion cooled the universe just enough for quarks to bind together into the first stable protons and neutrons. This set the stage for the main event. Big Bang Nucleosynthesis was a frantic, 3-minute burst of activity, a fleeting window from about 1 second to 20 minutes after the beginning. In that impossibly short span, the universe accomplished its first and most crucial act of manufacturing, forging the elemental palette of hydrogen and helium. And then, just as abruptly, the factory fell silent. The universe entered the Dark Ages, a profound silence lasting hundreds of millions of years where those first elements simply drifted in an expanding, lightless void. This quiet period was essential. It was the pause that allowed gravity to do its slow, patient work, gradually pulling those primordial clouds of hydrogen and helium into dense knots that would eventually ignite as the first stars. Their brilliant light ended the Dark Ages, flooding the cosmos with radiation in a process called reionization, and their explosive death seeded space with heavier elements. This stellar enrichment provided the grit around which the first galaxies could coalesce. Every single step in this cosmic chain was dependent on the one before it. The elements forged in the first 3 minutes were the fundamental seeds, the initial conditions that made all subsequent structure possible. Without that specific chemical legacy, there would have been no nuclear fuel for stars, no material for planets, and no foundation for the vast cosmic web of galaxies we observe today. Our complex cosmos did not emerge from chaos, but from a series of exquisitely well-ordered transitions, a cosmic symphony where the silent birth of elements was the crucial opening movement, setting the theme for everything that was to follow. This silent emergence of a predictable cosmos from a searing chaos touches on something profound. We see a universe that, at its very foundation, is governed by rules. The same mathematical principles that describe how a ball arcs through the air or how a magnet pulls on a piece of metal were in absolute command during the universe's first violent seconds. Every collision between a proton and a neutron, every fleeting existence of a deuterium nucleus, was dictated by these immutable laws. This is not a universe of random, magical happenstance. It is a cosmos of cause and effect, of probabilities and certainties, all playing out on the grandest possible stage. The fact that we can write down equations on a piece of paper that accurately describe the nuclear furnace of the entire infant universe is nothing short of staggering. It means the cosmos is comprehensible. Our human minds, products of that same cosmic evolution, have developed the capacity to understand the very processes that led to our own creation. We are not merely living in this universe, we are a part of it that has become self-aware, able to look back and decode its own origin story. This journey of discovery from a silent, hot beginning to the complex reality we see today is a powerful testament to the scientific method. It shows that through careful observation, rigorous logic, and a willingness to follow the evidence wherever it leads, we can uncover truths that are both beautiful and humbling. The order we find woven into the fabric of the cosmos, from the specific ratios of hydrogen and helium to the very laws of physics themselves, suggests a universe that is fundamentally knowable. And that may be the most significant whisper of all. Our cosmic detective story is far from over. The next generation of astronomical tools is now coming online, each one a more powerful ear pressed against the door of time. The James Webb Space Telescope is not just another observatory. It is a time machine designed to witness the cosmic dawn. Its infrared eyes are sensitive enough to catch the faint, stretched light from the very first galaxies as they ignited, ending the Dark Ages. By studying these infant star systems, we may see the indirect chemical shadows of the very first massive population, 3 stars imprinted on their light. On the ground, a new class of giants is rising. The Giant Magellan Telescope and the Extremely Large Telescope, with mirrors larger than any built before, will act like cosmic scalpels. They will perform ultra-high-resolution spectroscopy on the most ancient, metal-poor stars in our galactic halo. This is like upgrading from a standard microscope to an electron microscope. We will not just see that these stars are old, we will read their chemical autobiographies with unprecedented precision, measuring the exact amounts of primordial deuterium, helium, and lithium to a degree that was once impossible. Every decimal point in those measurements carries weight. A slightly different lithium abundance in a specific family of ancient stars could be the clue that finally cracks the cosmological lithium problem, pointing decisively toward new physics or a refined nuclear reaction rate. Beyond the stars, future space missions are planned to map the cosmic microwave background with even finer detail. These missions will measure the subtle polarization patterns in this ancient light, looking for the faint imprint of gravitational waves from the universe's first second, a time even before nucleosynthesis began. Each of these advanced tools has a single, unified goal: to reduce the fog of observational uncertainty. They will test the predictions of Big Bang nucleosynthesis with a rigor that borders on the impossible. And in doing so, they are almost certain to uncover new anomalies, tiny discrepancies that challenge our current models and force us to think more deeply. The quest to reconstruct the universe's first fusions is entering its most exciting phase. The silent whispers from the beginning of time are about to be heard with a clarity we have never before known. This delicate cosmic balance was a high-stakes competition between the universe's most fundamental players. On one side was gravity, the relentless force driving the expansion of the cosmos, relentlessly pulling matter apart and cooling the primordial fire. On the other side were the nuclear forces fighting to pull particles together against the tide. The strong nuclear force acted as the ultimate cosmic glue, struggling to bind protons and neutrons into stable nuclei. Had gravity been even slightly more dominant, the universe would have expanded too quickly, flinging particles apart before they could ever fuse. The nuclear assembly line would have been shut down before it even started. Conversely, if the force of gravity had been weaker, the expansion would have been too sluggish. The universe might have recollapsed in a great crunch, a gravitational reversal snuffing out the potential for elements in a single, catastrophic instant. The existence of that first deuterium nucleus was a testament to a perfect draw in this cosmic tug-of-war, a fleeting moment where the push and pull reached an exquisite equilibrium. But the nuclear forces did not fight alone. The electromagnetic force was a constant antagonist within the camp of creation. Every proton carries a positive electric charge, and like forces repel. For two protons to get close enough for the strong nuclear force to grab hold and fuse them, they first had to overcome this powerful electric barrier. They needed to be thrown together with incredible speed, a velocity that only the searing heat of the early universe could provide. This is why temperature was so critical. It gave particles the energy to smash through their mutual repulsion. And then there was the weak nuclear force, the quietest and most subtle of the four. It did not build elements directly. Instead, it acted as the universe's master fuel controller. In the first second, through a delicate dance involving neutrinos, the weak force carefully set the initial ratio of neutrons to protons. It decided how much fuel was available for building anything heavier than hydrogen. This precise ratio, 1 neutron for every 7 protons, was the direct result of the weak force's specific strength. A slightly stronger or weaker force would have left the universe with a completely different fuel mixture, altering the entire outcome of nucleosynthesis. The fact that we have a cosmos rich with hydrogen and helium, instead of one dominated by only hydrogen or choked with heavier elements, is not an accident. It is the direct and breathtaking consequence of a single, specific set of rules. The strengths of these 4 fundamental forces are not written on a sliding scale. They are fixed numbers, constants woven into the fabric of reality. Their exact values created a universe with a narrow window of possibility, a brief silence where the first elements could whisper into existence. Without this harmonious interplay, the cosmic symphony would have ended before its first note was played. Yet for all its triumphs, the silent birthplace of elements is not a closed book. The cosmological lithium problem stands as the most stubborn known discrepancy, but it is far from the only open question. The deeper we probe, the more we realize our reconstruction of the universe's first fusions is an active, ongoing investigation. Take the Barrian asymmetry itself, the universe's great preference for matter over antimatter. We know this imbalance happened, for without it we would not exist. But we still do not know how or why. The precise mechanism that tipped the scales, leaving behind that one part in a billion surplus of matter, remains one of the most profound mysteries in all of physics. Its origin likely lies in physics beyond the standard model, in conditions so extreme that the fundamental forces themselves behaved as one. Solving it would not just complete our picture of the first moments, it would revolutionize our understanding of reality's very foundations. Other speculative possibilities linger at the edge of our models. Could hypothetical primordial black holes, tiny and dense remnants from the universe's inflationary spurt, have drifted through the primordial soup? If they existed, their mere presence could have subtly warped the density of matter around them, creating local hotspots that altered nuclear reaction rates in their vicinity. Perhaps they even evaporated in a burst of radiation during nucleosynthesis, injecting extra energy that might have consumed some of the problematic lithium. Similarly, physicists wonder if the cosmos underwent dramatic phase transitions as it cooled, analogous to water freezing into ice but on a cosmic scale. Such shifts in the state of the universe could have created ripples in space-time or released energy, leaving a faint but potentially detectable fingerprint on the pattern of elemental abundances we see today. The path forward is one of ever-increasing precision. Our telescopes and spectrographs are becoming so sensitive that they are now testing the limits of the standard model itself. The current stunning agreement between theory and observation for hydrogen, deuterium, and helium is a monumental achievement. But what happens when we measure these abundances with 10 times the accuracy? Will that agreement hold firm, solidifying our cosmic story? Or will tiny, new discrepancies emerge, pointing toward physics we have not yet even conceived? These are not signs of a theory in crisis. They are the exciting frontiers of science. Every unanswered question is a beacon, illuminating the path to a deeper understanding. The silent birthplace of elements, for all we have learned, still guards its deepest secrets, and it is this enduring mystery that continues to drive the most ambitious experiments in cosmology and particle physics, ensuring that our quest to reconstruct the universe's first fusions is a story still being written. Our journey to reconstruct the universe's first fusions reveals a story of breathtaking precision and profound consequence. Every atom of hydrogen in the water you drink, every nucleus of helium that lifted the first airships, was forged in that frantic 3-minute window. From the formation of the first, fragile deuterium nucleus to the helium that would later fuel the nuclear furnaces of the first stars, this silent birthplace set the entire cosmic narrative in motion. It provided the raw, chemical vocabulary for everything that was to come. The remarkable agreement between what our equations predict and what our telescopes observe is not just a scientific success, it is a pillar of modern cosmology. We can point to the oldest stars and the faint glow of the cosmic microwave background and say, with confidence, that we understand the recipe for the infant universe. Yet, stubborn puzzles like the lithium problem are vital reminders that the cosmos has not yielded all of its secrets. These discrepancies are not failures but guideposts pointing toward deeper layers of physics we have yet to uncover. The elements forged in those first 3 minutes are the ancient heritage of every atom in your body and our world. We are literally made of the universe's first creations. As we build ever more powerful telescopes and particle accelerators, we draw closer to a complete understanding of our ultimate origins. So the next time you look up at the night sky, reflect on this incredible connection. You are gazing at a cosmic story that began with a silent, elemental forge, a story that led across billions of years directly to you.